I'm happy to have Professor Anish Dawar from Cambridge University. I think he's working in finite model theory, which is a kind of area between model theory and complexity theory and computability. And he's going to talk about model theory of 10 classes of finite structures. Okay, please welcome Professor Anish Dawar. Okay, you can start.
Okay, thank you very much for the introduction. Thank you very much for the invitation to speak at your seminar. This is, in fact, my second occasion speaking at the IPM. The last one was, I was there for a conference in person in 2015. This time I can only be there virtually. But it is a pleasure and an honor to talk to you. And so I'm going to be talking about the model theory of 10 classes of finite structures. I should say that I gave a sort of 3-hour tutorial on this summer at the Logic Colloquium meeting in Gothenburg in Sweden. And this is a sort of shortened version of that 3-hour tutorial. I will shorten it to 90 minutes. And I understand the aim is I will take a short break after about 45 minutes. Okay, so as you mentioned, the finite model theory is sort of this subject somewhere related to classical model theory and to complexity theory. So complexity theory being concerns arising in computer science. So I think, I don't know the exact history. I've not been able to trace who came up with the name finite model theory, but it came to be used in the 1980s. To describe this field, where the object of study, the aim is to understand the expressive power of logic on the class of all finite structures. And the logics of concern include first-order logic, second-order logic, many intermediate logics between first and second order, some going beyond second-order logic. And in some sense, the motivation for this study comes from computer science, especially complexity theory and database theory. The point is that many problems that arise in these areas of computer science can naturally be formulated as questions about the expressive power of logics. And when we're interested in their expressive power, but the structures involved in computation are necessarily finite because we're dealing with structures which can be presented as input to some computational device. The methods that came to be developed in this subject bear only a distant relationship with classical model theory. I mean, we are interested in studying the expressive power of logics, like in classical model theory, but they came to use very different methods. But in recent work, there's been more of a convergence, and some of the ideas that arose in the classification project of stability theory have started to find applications in finite model theory. And this is the topic I want to get to explaining in this talk, this kind of convergence of ideas, of model theoretic ideas in the study of finite model theory. So back in about 1993, Fokion Kalaitis gave a tutorial on finite model theory at this LICS conference, Logic and Computer Science, major conference on the topic. And he identified, he looked at this, what was then the new subject of finite model theory, and he classified the results into 3 different trends. The first was what he called the negative results. There was a lot of work showing that many of the classical model theoretic results and methods don't work if you only consider structures to be finite. And this includes, you know, the compactness theorem, the completeness theorem, various interpolation and preservation results, and so on. There was a second trend he identified as conservative, which is showing that certain classical model theoretic results do hold when you restrict yourself to finite structures. So while compactness may not work, some consequences of compactness couldn't work. And I mean, he identified things like monotone versus positive inductions, which were shown to have the same expressive power, which is, you know, related to Linden's preservation theorem in classical model theory, but the exact form of Linden's preservation theorem doesn't hold. And he identified locality, which is a method of classical model theory, though not much used there, which works in the finite and in fact becomes one of the central methods, as I will explain in a bit. And the third trend he identified was what he called the positive. There are concepts and results which are specific to finite structures, which don't necessarily make sense in the classical setting where structures can be infinite. And in this, he identified descriptive complexity, so the connection with computational complexity, and 0-1 laws. I won't say much about 0-1 laws in this talk. In fact, I don't think I won't say anything beyond what's on this slide now. One of the key things I will explain is the ideas of locality, and I will relate them to complexity to some extent. Okay, so in a sense, maybe can I write on here? Yes, locality and descriptive complexity. I will say a little bit more about. So let me start though by saying a little bit about this the negative aspects. So in classical model theory, in fact, the compactness theorem is the beginning of much work on the subject, right? And if we insist that our structures are always finite, the compactness theorem is simply not available as a way of constructing structures. And here is just sort of a simple illustration. Write down for each natural number n a sentence which says that there are n distinct elements. This is a collection of sentences which has no finite model by construction, but every finite subset has a finite model, right? So it's satisfiable in the finite. And therefore, we conclude that we don't have anything like a compactness here. So compactness, in a sense, fails. Many of the consequences of compactness also fail, right? And here is one example, which was an early result in finite model theory. So here's a classical result of model theory, the Weierstrassky preservation theorem, or sometimes called the existential preservation theorem. It can be formulated in this way. A sentence of first-order logic, let's say, is equivalent to an existential sentence, so one which only uses existential quantifiers positively, if and only if the models of the sentence are closed under extensions. So this, like, most preservation theorems, it relates a syntactic notion, being equivalent to an existential sentence, to a semantic property of the class of structures, namely being closed under extensions. And the one direction of this equivalence is kind of obvious in the sense, if your formula is equivalent to an existential sentence, existential sentences are always closed under extensions because the witnesses to the existentials are still available in the extension.
Are you meant by existential or universal? Because universal are preserved under extensions, not existential.
So universal are preserved under substructures, existential are preserved under extensions. So what I mean by this is, if you have a structure A and it is extended to B, by preserved under extensions means A satisfies phi implies that B satisfies phi.
Okay, sure.
Right, that's what I mean by preserved under extensions. Okay?
Yeah.
So the models are closed under extensions, meaning whenever you have a model, any extension is also a model.
Right.
So, so the syntactic implies the semantic, and there, doesn't matter whether your structures are finite or infinite or so on. But the proof that any sentence whose models are closed under extensions is equivalent to an existential one crucially uses the compactness theorem. And now this is maybe not so obvious, it fails when you restrict your structures to be finite, okay? So this was already observed by Tate back in the 1950s. So the idea is the following. You consider relativization. So I say expressive completeness, sorry. So when I talk about preservation theorems, as I said, relate a syntactic notion to a semantic one. And I call the direction from right to left the expressive completeness, saying that the syntactic form is complete, expressively complete for the semantic restriction. Now, if you relativize to a class of structure C, the statement becomes something like this. If a sentence satisfies the semantic condition restricted to C, in other words, for instance, if a sentence is preserved under extensions among structures in the class C, then it is equivalent, again, on the class C to a sentence of the syntactic form, for instance, existential, right? So for semantic condition, read preserved under extensions. For syntactic, read existential. The point is that if you make the class C smaller, you weaken the hypothesis because you're only requiring some closure under restricted to C, but you also weaken the conclusion because you're only requiring equivalence on C. And so you can't conclude anything about whether the sentence holds on a class C. I mean, from that you can't, whether this expressive completeness condition holds on the class C doesn't allow you to conclude anything about a subclass. In particular, it's known that the Weierstrarsky fails when the class is the class of all finite structures. In other words, there is a sentence of first-order logic whose finite models are closed under extensions, but it is not equivalent to an existential sentence. Okay, so this was observed by Tate. But the class of all finite structures is badly behaved, but then there may be, you can restrict it further and it may become true again, right? Because again, you can't conclude its truth on a subclass or even its falsity on a subclass from whether it's true on this. So one conclusion is that the class of all finite structures is not well behaved in a model theoretic sense. This was a point made to me, I remember when I was a student by John Barwise. He said this is just, as he put it, finiteness is not a natural condition. But anyway, the point that I want to make is that some good model theoretic behavior can be recovered by restricting ourselves even further. So the title of my talk refers to tame classes of finite structures. So instead of all finite structures, consider restricted classes, and you get sometimes good tame behavior. Let me give you an example. Consider the class of finite graphs. So graphs are just finite structures with one binary relation. And for a natural number d, BDD means the class of finite graphs of degree at most d, right? So this is degree bounded by d. In other words, every node in your graph has at most d neighbors, okay? At most d things it's related to. And in a paper some years ago with Albert Atzerius and Martin Grohe, we proved that this extension preservation holds when you restrict yourself to bounded degree graphs. So graphs of degree at most d. And so I talk about graphs, but the result is really, I mean, we use the kind of graph theoretic structure to prove the result, but it really holds for any kind of relational structures where every element is related to at most d others. The proof, rather than compactness, uses the locality of first-order logic. So I mentioned locality rather than compactness is a property that survives the restriction to finiteness and becomes a key tool in finite model theory, as opposed to, say, the compactness which is not available. So now I want to explain to you what locality is, what I mean by the locality of first-order logic. And this is defined in terms of, and this, I mean, I think this is a good example because it relates relational structures to an underlying graph, right? This is known as the Geisman graph of a structure. So for a structure A, so for now, I'm going to consider structures A always in a relational vocabulary, right? So you can develop this whole theory in the presence of constant and function symbols, but it'll be much simpler notationally if I just stick to relationals, to relational vocabularies. So we just have a collection of relations. I have a structure, The Geisman graph of the structure is a graph, an undirected graph, which means a set of vertices with a symmetric binary relation on them. The vertices of the graph are the elements of the structure, and the binary relation is given by this. There is an edge between U and V, if and only if there is some relation in this vocabulary which includes a tuple, including both U and V, right? So U and V are related by some tuple in some relation. So this is just the connectivity graph of the structure, you know, how the elements are connected to each other by these relations. And when I say we're going to define tame classes of structures, we're going to define these classes by restricting the structures according to their Geisman graphs, saying that their Geisman graphs must come from some particular class of graphs. For this reason, it's very convenient to often just talk about graphs, and I will often do that. And I'll make this explicit in a little bit. In fact, let me say it now. I'll restrict myself to relational vocabularies with one binary relation and a collection of unary relations. So these can be thought of as colored graphs, right? So you have a graph, you have one binary relation on the vertices, and you have colors, which are unary relations, which color the vertices. This is sort of the simplest setting in which we can formulate the results. But as I said, they apply more generally to structures if you formulate the results in terms of the Geisman graph of the structure. Okay.
So in this case, the Geisman graph is going to characterize the whole structure, right?
So, sorry, I mean, it's a bit faint. I didn't quite hear that.
So in this case, when we restrict ourselves to vocabularies with one binary relation, it means that the Geisman graph is going to characterize the whole structure, right?
Well, yes, in a sense. Okay, in a sense, no. You do lose some information still going from the Geisman graph because my one binary relation doesn't have to be symmetric. So the Geisman graph takes its symmetric closure. And I'm forgetting, in the Geisman graph, I'm forgetting all the unary relations. So the Geisman graph still tells me the connectivity of the structure, but there is some loss of information in going from a structure to its Geisman graph, right? So let me give you a little map. So, you know, back in about 15 years ago, I had an article where I reviewed what I call the model theory of the tame classes. And there was a map of various ways of restricting the Geisman graph to sparse, to certain kind of sparse graphs, so very sparsely connected structures, which gave tame classes. The second half of my talk today, I will basically get away from the sparsity condition and tell you about recent work on characterizing structures where the underlying Geisman graphs are not sparse. But let me give you a map for, in some sense, where the world was about 15 years ago, a classification of various tame classes based on their Geisman graph. So this is my map. And let me just kind of point out a few things. So some simple ideas. Bounded degree is something I mentioned before. So a class of graphs has bounded degree if there is some constant bound D such that every graph has no more than D neighbors, right? Class of graphs of bounded degree are tame in a certain sense. And I gave you one example that, you know, the kind of extension preservation theorem holds. I will give you more. Here's another one, which you might be familiar with, the class of planar graphs, right? Those graphs which can be embedded in the plane. That's a nice, well-behaved class. It turns out it has various tameness properties. It can be generalized to bounded genus, those graphs that can be embedded into some fixed surface. This can be generalized further to graphs which exclude a fixed minor, and I'll say a little bit more about exactly what that means. I mean, I'm not going to define all of these concepts. There's, you know, there are different graph parameters, tree depth, tree width, which you can limit, and they give you, you know, sort of certain well-behaved tame classes. And all of this, the most general one I will talk about is nowhere denseness. And for this one, I will give you a formal definition in a moment. And in some sense, there was sorry?
Can I ask a question?
Yes, please.
So in this context, actually, the What do you mean by tame? It means that in the sense of tameness of the Geefman graphs, or in terms of the stability things?
Okay, so I will. I haven't. You're absolutely right. I haven't defined notions of tameness. I'm using it as an informal notion, meaning they're well behaved. But let me say two things. So, right, we're taking classes of structures and we're restricting their Geefman graph. And this is all of these are restrictions on the graph, on the Geefman graph. We say that the class of graphs is has bounded expansion, or the class of graphs is nowhere dense. These are all based on restrictions on the graph. They give rise to certain notions of tameness, and I will talk about two. One is, I mentioned examples that they have nice model theoretic properties, like preservation might hold or something like this. But I will talk about algorithmic tameness, and I'm going to come to that in a moment, which means that certain computational problems are easier, which are hard in general, become easy when you restrict yourself to classes of structures like this. And then in the second part of my talk, you will see that this notions of tameness actually are related to stability theoretic notions of tameness. Okay? And in fact, my argument is that stability theory provides the natural way to generalize from these, which are classes of sparse graphs, to classes of graphs which are not necessarily sparse. That'll be the argument in the second part of the talk. I hope that answers your question for now.
Yeah, sure. Yeah, thanks. Yeah.
Okay. So, I mentioned algorithmic tameness. Let me be specific about this now. So these restricted class of graphs have been much studied in a field of parameterized complexity, which is a sort of study of algorithms on graphs, because they're algorithmically tame. And eventually I want to tie this, as I said, to notions of stability theoretic notions of tameness. So what does algorithmic tameness mean? It means there are problems that are hard in general for which you can find efficient algorithms when you restrict yourselves to a tame class. Let me give you one such example. So here is an algorithmic problem. The input is a graph G and two positive integers L and R. And the question the algorithm has to decide is, in the graph G, can you find L distinct vertices such that their pairwise distance is at least R? Okay, so can you find a set of L vertices which are all far away from each other, where far away is given by the parameter R? Now, this problem is considered computationally hard in the sense that it's NP complete. If you're familiar with the notion of NP completeness, I hope this statement is precise. If not, take it as meaning that we don't expect to find efficient algorithms for this. And under reasonable assumptions, you can you can prove so reasonable, because in complexity theory we don't have absolute lower bounds. You have to make assumptions. You can prove that there's no algorithm that solves this whose running time is n to the power of something smaller than L, right? So there is an obvious algorithm which simply looks at every subset of the, so here n, I should say, n is the number of vertices in G. So the number of vertices in G. So there's an obvious algorithm where you look at every subset of the graph of size L, and you look at the distance between them. You can just explore the graph and see what the distance, pairwise distance between them is, and run through all n choose L possibilities. And this will answer the question. So the running time of this algorithm, something like n to the order L, and the assumption under reasonable complexity theoretic assumptions, you can't do anything better than that. You can't do anything faster than that. But if you restrict yourself to tame classes like the classes I had on the previous slide, you can do it. You can give an algorithm whose running time is some function of L and R, so independent of the size of the graph, in other words, times n raised to the power of constant c, where c now is independent of both L, R, and n, right? So c is a constant. In fact, for most of the examples we will look at, you can make this constant close to 1. You can make it less than 2, let's say. So this is what we consider an efficient algorithm. It's not necessarily what we would call a polynomial time algorithm, because I'm putting no restriction on what the function f is. It may be exponential or even doubly exponential in L and R, but the dependence on n is simple, right? It's sort of what we call, I mean, it's the dependence on n is polynomial. And in fact, in all our examples, it'll be subquadratic, right? So this has been identified as a key notion of algorithmic tameness. You know, the hard problems are easy on the class and easy in exactly this sense. This is what's called parameterized complexity. Okay. The point is, the connection to logic comes by the fact that there's a sort of explanation in logic for the algorithmic tameness of these classes. In that you consider the following algorithmic problem, a more general one, rather than just, I mean, my example of the previous one was a scattered set. But I consider now the algorithmic problem of evaluating a first order sentence, so a sentence of first order logic in a finite structure, right? So this is like algorithmically a very basic problem in logic. As an input, you get a structure A, some finite structure, and you get a first order sentence, and you have to say yes or no, is this sentence true in the structure, right? It seems like, you know, I mean, from the point of view of logic, this is a fundamental algorithmic problem. What do we know about how hard this problem is? Well, again, we can come up with an algorithm whose running time is bounded by something like this function. L here is the length of the formula phi. N is the number of elements of A. And M is the nesting depth of quantifiers in the formula phi. I mean, you could do a more careful accounting, and I said you can do the number of distinct variables, but let's not worry about that. So the point, the way you do this, I mean, this is again the kind of naive way of evaluating the formula. For every quantifier, you create a loop which runs through all possible elements of the structure, and you recurse on the structure of the formula. The length of this parameter L accounts for the recursion, but you know, basically, if you have quantifiers depth nested to a depth of m, then you have m nested loops, each of them running through all n elements. So you get running time something like n raised to the power of m. Okay, this is, as I said, the most naive way of evaluating whether the formula is true in the structure. Question is, if we restrict the class of structures, can we do better than this? In particular, what we don't want, we don't want an exponential dependence. I mean, we don't want, and here, you know, you get the size of the structure raised to the power of something which increases with the size of the formula. Just like with the scattered set, you know, that's what we want to avoid. And it turns out that we get, for most of the classes I had that I call tame classes, it turns out you can do better. The most general result on the tractability of first order satisfaction in sparse classes is the following result, the theorem of Grohe, Kreutzer, and Siebert. For any nowhere dense class, and remember, nowhere dense was the most general class on my map. For any nowhere dense class of graphs, and any positive epsilon, there's an algorithm deciding whether a sentence is true in a graph from this class, whose running time is some function of the length of the formula raised to the power, as I said, n to the 1 plus epsilon. So you can get it down as close to 1 as you want, right? So the dependence of running time on the size of the graph is almost linear, right? Though the function f might be very bad, right? So we're kind of focusing on how the algorithm depends on the size of the graph. Okay. So
Sorry, what was L here? What was L here?
L here, it says L is the length of the formula.
Ah, I see. Okay.
Right?
So it doesn't depend on the quantifier complexity or anything, just the length of the formula.
Yeah, so though of course L is a bound on the quantifier complexity also.
Yeah, of course.
So, so yes.
Yeah.
Okay. So that's the So this is the result which shows that the lower dense classes are tame. And now you see that, okay, my example of the scattered set problem, right? That the problem of finding an R scattered set of size L is actually a sort of special case of this, in the sense that for any fixed R and L, you can write a formula, right? Which says that there exists, x1 up to xl, and then the conjunction over I not equal to j of something which says that the distance of xi and xj is greater than r, where this formula that says that the distance is greater than r can be written as a first order formula. Okay, so you see that from this Grohe-Kreutzer-Siebert's result, it follows that there's an algorithm for any fixed. I mean, there's an algorithm which looks at finding an R scattered set of size L, which is bounded by some formula whose running time is bounded by some function of L times R, because the length of this formula is bounded by both L and R. Is bounded by, some function of L and R. And then the dependence on the size of the structure is almost linear, which is much better than, as I said, the general case when you don't restrict yourself to lower dense graphs, where we know that you can't do much better than n to the L, which means trying all L element subsets, right, for witnessing this. So I hope you see the difference between the algorithmic tameness of this class and the hardness of the problem in general. Okay. So here, just as a recap, is this map again. Now, this result has been proved for lower dense classes, and so it implies it for all the other classes on this map. The result was a culmination of work, where I think, the first results were for bounded degree in the early 90s, and bounded tree width as well. They were generalized to excluded minors, bounded local tree width. Then the locally excluded minors was a paper in about 2007. And the bounded expansion and lower dense results followed soon after that, about 2013, 14. Okay, but now this is in some sense the limit, and there's a formal sense in which you can show that for among sparse classes, and I will say what that means, you can't really go beyond the lower dense. Okay, but I want to give you an idea of the method of proof and how it uses the locality of first order logic. And I will, rather than this, I will give you a simpler case, which is the bounded degree graphs, because I think this will this kind of illustrates the method. So, as I said, it depends on the locality of first order logic. So let me define what I mean by that. And I'll state the Geifmann's locality theorem, which is the kind of engine of this. So I've already kind of used this implicitly. You can write down a first order formula with two free variables x and y, which says that the distance between x and y is greater than d, right? In the distance in the Geifmann graph, that is. So I will abbreviate that formula by saying delta xy is greater than d. Now, if you have a formula psi with a free variable x, now I write psi superscript rx, where r is now again a natural number parameter, to denote the formula obtained from this formula psi by relativizing all the quantifiers to elements which are a distance at less than r to x. Okay, what that means is whenever you have a subformula, there exists y theta inside psi, you replace it by saying there exists a y, a distance at most r to x and theta, and every subformula for all y theta is replaced by saying for all y whose distance from x is less than r, theta r must be true, right? So in other words, this is simply saying that psi is true. I suppose I actually don't need the free variable x here. But anyway, psi is true in the R neighborhood of x, right? So in the substructure induced by those elements whose distance from x is at most R. Okay. A basic local sentence is defined to be a sentence which says that there are S elements whose pairwise distance is greater than 2R. In other words, their R neighborhoods are disjoint. And in the R neighborhood around each point, the formula psi is true, right? So in other words, psi, yeah, the formula psi holds. So we can find S points pairwise far apart, and around each one, the formula psi is true. Okay, so you see this is a much more general form of the particular problem of finding finding an R scattered set of size S. Because we're okay, is it clear what I mean by basic local sentence? So the theorem of Geifman, this dates again to the 1980s, and this is not specifically about finite structures, but this is the locality theorem, as I said, which becomes the key engine of proof in finite model theory, is every first order sentence can be expressed as a Boolean combination of basic local sentences, right? So what this is saying is that anything you can say in first order logic is really saying that there exists enough elements of certain local type. You can talk about the local neighborhoods of elements, and you can say that there are certain number of such local neighborhoods, or you can say that they're not there and you can do Boolean combinations of these things, but that is pretty much all you can do in first order logic. Okay. That
for formulas, right?
Sorry?
Assume that this is also true for formulas, that any first order formula is a Boolean combination of
basic local formulas. Yes. So in fact, you could say something stronger. Any first order formula is equivalent to a Boolean combination of just local formulas like this and basic local sentences, right? So I mean, the formula is really saying something about the local neighborhoods of some points, plus that some basic local sentences hold in the larger structure. So yes, but I mean, that's really a stronger form of the formulation you gave. That's right. So what we call this the Geifman normal form of the sentence. I mean, there's a slight misnomer because it's not really a unique normal form, but basically any sentence can be converted into such a Boolean combination. And actually, it's implicit in the proof. Geifman didn't state it, but you can actually, I mean, there is an algorithmic process which can convert any first order sentence into an equivalent Boolean combination of basic local sentences. Okay, so that's the locality theorem. And we want to use this. As I said, I'm going to use this to illustrate a theorem first proved by Cese, though he used a different argument. But we can use Geifman's locality theorem to prove that whenever you have a sentence of first order logic, right, and you fix some constant d, then the problem of evaluating the sentence in a graph where degree is bounded by d can be done in linear time. Okay, so by linear time, I mean, so again, there will be some function of d, which we're treating as a constant because d is fixed, times the size of the graph, and the exponent here is 1. Okay? So crucially, you're not raising n to the power of something that depends on the formula. Okay, so that's Cese's theorem. And I want to give you a proof of this using Geifman's locality. I'll keep an eye on the time. So yes, so this is actually what I said. So this can be done in time, which is some function of the length of the formula times n, right? I mean, so really it's the length of the formula, and it's f of L and d, I should have said, but okay. So first thing, as I said, the first thing the algorithm does is start with the formula and convert it into Gaussian normal form. This doesn't depend upon the structure at all, so the running time is entirely independent of n. Once we have a normal form, we have to just evaluate each basic local sentence that appears in it in the graph, and then doing the Boolean combination is again something that is independent of the graph. So to prove the theorem, it suffices to prove it for basic local sentences. Okay, and that's what I'll do. So the idea is I'm given a structure A, or a graph, as you will. So, okay, now this is just introducing a piece of notation. I've already used it, in fact. NRA is the neighborhood, those elements that are a distance of most R from A. And for a set of elements, I refer to the R neighborhood of S as, the union of the neighborhoods of the individual elements. And I will write the neighborhood AR in A to denote the not just the set of elements, but the substructure induced by the set of elements, okay? But it's a substructure expanded with a constant for A itself, right? So we're looking at the R neighborhood, but we're distinguishing the element A with some constant. That's what we call this R neighborhood, okay? So given a graph with degree at most k, and given this basic local sentence, how do we evaluate it, right? So remember, what we don't want to do is try all possibilities for these, because that would be time n to the s. We want to avoid it. We want to do this in linear time, okay? So we don't want to try all possibilities for these neighborhoods. But look at what we're trying to look for, right? We're trying to find s points which are pairwise far apart, and where for each point in the neighborhood, this formula psi holds true. Well, we start by looking at each element and determining whether the neighborhood satisfies this formula, okay? Now, because we have bounded the degree to be k, the neighborhood of radius r around an element has size bounded by something like k raised to the power r, right? Which for our purposes is a constant. It doesn't depend upon the size of the structure A at all. So evaluating this is easy, right? This is essentially bounded time. We do it for every, sorry, I should call it A, right? We do it for every element of A, so that takes linear time, right? For every element of A, we do a constant amount of work. Okay. So label A red if this is true, and don't label it otherwise. So now the problem has reduced to one we'd kind of looked at before. We want to know whether there exists a scattered set of red vertices of size s. We want to know whether there exists s vertices which are all labeled red and which are pairwise far apart, because that's what the sentence says. Okay. Again, but we want to do this without trying every subset of size s. We want to do this in linear time. So how do we do this? Here's the idea. We look at the red vertices of A. We know which ones are red. And we take them one by one in any order. Pick a vertex, a red vertex, and remove its entire neighborhood of radius 2r from the structure, and see if there's still another red vertex in there. If there is, choose that one and remove its neighborhood from the structure. Note that when you're removing the neighborhood, you may be removing other red vertices. But you carry on. If this process continues for s steps, we're done. We have found our 2r scattered set of size s, and we can say, report, yes, there exists such a set. But if it stops before s steps, we don't know, right? Because it may be that we just made bad choices And a different sequence of choices would have found us S elements all far apart. But what we can conclude, if this process stops at some stage U before S, it means that we have found U elements such that when you remove their neighborhoods, there are no more red vertices left. In other words, all red vertices are in the 2R neighborhood of this small set of U elements. But now this thing, the neighborhood, 2R neighborhood of U elements, where U is less than S, is something of size at most S, right? Well, because U is less than S, times K, the degree bound we had, to the R, right? It's the union of neighborhoods of at most S elements, and each of these, S, K, and R, is a parameter that's bounded. So in other words, to determine whether within this there is a 2R scattered set of red vertices, we can just do by exhaustive search. Here we can try every subset of S elements because we're looking at subsets from a bounded size set. That's it. That's the whole proof that the evaluation of first order sentences in bounded degree graphs can be done in linear time. And this kind of strategy is what's used for all these tame classes. The overall strategy for evaluating a sentence is to convert the formula to its Geisman normal form. And then for each basic local sentence in the Geisman normal form, evaluate the local formula in the neighborhood around every element. And then determine whether there is a large enough scattered set among those elements that satisfy. So here we used the bounded degree property to do both these things. The evaluation at a local formula, because we said that the things have bounded size, and finding the large enough scattered set, because we found that if, again, we could restrict to a set of bounded size because of the bounded degree requirement. In general, for these other tame classes, you don't get things of bounded size, but the whole idea is to show that these local neighborhoods are sort of structurally simpler than the whole thing, and that this problem of finding large scattered sets can be done in some efficient way. Okay, so here is the map. I basically, as I said, I gave you pretty much a full proof for why the evaluation of first order formulas, which is kind of our benchmark for tameness, holds in the bounded degree case. The proof for nowhere dense is much more involved, and I'm not going to give it to you. But what I do want to move on is tell you what nowhere dense means and give you a precise notion, and then move away from sparse classes. But I think I said I would take a brief break at 45 minutes, so this seems like a good time to do that. Maybe?
Yes, okay. So how about 15 minutes break? Is that okay?
Sure. Yes, okay. This is quite up to you.
So we will resume.
Sorry.
Thank you very much.
Okay, resume in 15 minutes.
Is there any chance to ask a question here?
Yes, of course.
Okay, so first, in the definition of Geffman graphs, actually, it is. It seems that it has the potential to lose a lot of information. For example, assume that the graph is basically a half graph. You have two R1 and R2. The first one is just basically a half graph, and the other one is just a complement, right? So both are very rich and structurally very important relations. But once you combine those together with the Geffman graph, basically what you get is just a complete graph, right? So it's basically loses all of the information, destroys all of the information. So
you're absolutely right. Yes.
Yeah. So it seems that it could have been defined in a more, in a way that it stores more structural information, right? So,
no,
but it
okay.
doesn't.
So I think I think you have put your finger on a very important point, and this will be I will address this in the second half of the talk. Okay, this very point.
Okay.
So the point is that the Geisman graph allows us to, going to the Geisman graph allows us to use this locality theorem, and for structures which are sparse in the sense that their Geisman graph is, doesn't have a lot of edges, this locality gives us exactly the right tool. To move beyond sparse structures, and this is what I will do in the second half of the talk, we need to look not at the Geisman graph, but what graphs you can interpret in your structure, right? And I mean, we will really talk about, if you will, the Geisman graphs of structures which can be interpreted in your structure. And that's, I think, will address exactly the point you're making.
Yeah, sure. And just quickly, can I second, because it is relevant to the proof that you mentioned, right?
Yeah.
So in the second part of the proof, actually, you use the, well, first, both parts actually uses the idea of somehow bonding the neighbors, balls, the size of the balls, because of this
That's right.
bonded, right?
Yeah.
But in the second proof, actually, it seems to me, actually, maybe I vaguely feel that we are losing something, some resources, right? Because we start to assume that we, in very, very early stops, in the procedure of eliminating that neighbors, stops in very, very early stage, right? So it means that the center that we have already chosen is not a good one, because it's very close to many things, right? So but still we are checking a lot of things, right? So so my question is, wait, but it seems to me that the algorithm could be improved somehow in here. I don't know if eventually it will lead to a better complexity, but at least we can eliminate certain, and then we start immediately, we start doing exhaustive search, right? So
no, you're right. So look, this is, you're right. I mean, this is, I'm not trying to optimize this algorithm. This is aimed at establishing a linear lower bound, just to show that you can do it in linear time. In other words, the exponent of n doesn't depend on, you know, rs or, you know, any of these other parameters. I'm sure, you know, if you wanted to, in practical terms, this could be optimized further.
Okay.
This is, you know, this is meant to be a proof of linearity rather than finding the best algorithm.
I see. Yeah. Okay. Thanks a lot.
Okay. Thank you. So this is, I concluded with this map, and I want to next tell you what this nowhere dense classes are, and also somewhat justify the name. Even though I'm not going to prove to you anything specific about this. So the definition of nowhere dense is based on the notion of graph minors, right? Because it is, in some sense, was generalizing this idea of an excluded minor classes. So very briefly, let me review what graph minors are. I mean, there's a very rich theory around the structure of the graph minor relation, which you may know about. But we say that a graph G is a minor of a graph H if you can get G from H by repeated applications of these three operations: deleting an edge, deleting a vertex and all its incident edges, and contracting an edge, where contracting an edge is the following operation. You contract this edge by identifying the two vertices at its endpoints to make a single vertex whose neighbors are the neighbors of those two apart from each other, right? This is contracting an edge. So basically, if you can start from G and by repeated operations of deleting and contracting, get to H, then we say H is a minor of G. Another way of saying this is the following. G is a minor of H if you can find a subgraph of H, so a subset of the vertices and a subset of the edges, with a surjective map to V, to the vertices of G, so that the pre-image of every vertex in G is a connected subgraph of H prime. And for every edge in G, there is an edge in F prime between some vertex in the pre-image of U and some vertex in the pre-image of V. This seems like a complicated thing, but maybe a simple example will illustrate. If G is a graph on the complete graph on three vertices, right? That's your G. What does it mean for G to be a minor of H? It means in H we can find three disjoint connected subgraphs such that there's an edge from somewhere in there to there, somewhere in there to there, and somewhere in there to there, right? That's really what it means for G to be a minor of H. We can find G structurally inside H in this form, right? Because if you have such a thing, then you can contract all the edges inside this, and inside this to get exactly G, deleting everything else. Okay. We say these subgraphs, so these subgraphs meaning these things like these little blobs I've written over here, right? So in here, we have a map from H, from a subgraph of H to G. We've deleted everything outside of these. And the map takes this to this vertex, everything in here to this vertex, and so on. So the pre-image of a vertex in G is some connected subgraph in H. And we call those the branch sets, which are witnessing this minor. And if those branch sets all exist within neighborhoods of radius at most R, then we say that G is actually a minor at depth R of H, right? So now we've parameterized the minor relation by a positive integer, which says basically, you know, when you do the contractions, they all occur within neighborhoods of radius at most R. So here's the definition of what a nowhere dense class is. A class of graphs is nowhere dense if for every R, you can find some graph which is not a minor at depth R of any graph in C. So, yeah, that's right. Okay, so it generalizes the notion of an excluded minor in the sense of, I mean, well, okay, a nowhere dense class doesn't necessarily, the excluded minor classes are those where some fixed graph is forbidden as a minor. For instance, the planar graphs are exactly those in which K5 and K33 are forbidden as minors. And we, so we generalize that to taking any collection of graphs and excluding as minors. Nowhere dense is broader in that, okay, you don't necessarily have to forbid a graph, but for every fixed radius, there is some graph that is forbidden as occurring as a minor at depth R. Okay. Why is this significant? Well, this notion was introduced by Nechetrela and Osona de Mendes as a formalization of what makes classes of graphs sparse. So these nowhere dense classes have the property that the number of edges in a graph is small in the sense it's, okay. In general, an n vertex graph can have as many as, you know, n squared edges or n choose 2 edges. In a nowhere dense class, every graph has, I mean, the number of edges can grow at most, you know, n to the 1 plus something very small, and 1 plus epsilon. And it's nowhere dense in the sense that you can't find any subgraphs either which are dense. And this fact is formalized in a lovely theorem. Okay, I have this definition. I'm not going to use effectively nowhere dense, so let me just leave that. So the fact that nowhere dense classes are exactly the sparse graphs is summarized in this beautiful theorem by Nechetrela and Osona de Mendes, which goes like this. Take a class of graphs, any class of graphs, so an infinite class of finite graphs, and associate it with this parameter. Okay. You look at the number of edges so this double vertex means the number of edges, and this is the number of vertices. So you take the log of the number of edges divided by the log of the number of vertices. You take CR is a collection of graphs which are obtained as minors of a graph by contracting neighborhoods of radius at most R. So you look at, so note that this log G over log of the number of edges over log of the number of vertices is at most about 2, right? Because you have at most n squared edges and n vertices. But now you look at all the graphs you can get by contracting, right? So you get, in some sense, richer classes of graphs as R increases. And you look at the lim sup of this and look at the limit as R increases of this lim sup. Their theorem says that this parameter on any class of graphs can take only 3 values. For every class of graphs, the limit as r goes to infinity converges to either 0, 1, or 2, and nothing else is possible. The nowhere dense classes are exactly those where the limit is either 0 or 1. Okay, so that's the sense in which they are nowhere dense. You cannot create a dense graph by contracting neighborhoods, or you cannot create a dense class of graphs by contracting neighborhoods of a fixed radius. Okay, that's that. I just wanted to sort of mention this theorem. So that's, in some sense, shows that these nowhere dense classes are really the limit of tame classes you can get by forbidding dense configurations, right? Forbidding configurations which are fairly dense in the Geisman graph. So now, to consider tame classes beyond that, we want something other than Geisman locality, and this was kind of exactly alluded to in the question we had right at the end of the first half. So I want to sort of do a quick review, right? So Geisman's theorem tells us that every first-order sentence is equivalent to a Boolean combination of basic local sentences. And this makes a lot of sense when your Geisman graphs are sparse, because local neighborhood sparsity means your local neighborhoods are simpler. They're small parts of your whole graph, right? So to evaluate a formula, it suffices to look at local neighborhoods. And if the local neighborhoods are structurally simpler, this gives us a recursive procedure for evaluating a formula efficiently. That's been the kind of general thrust of the tameness of sparse classes. But sometimes local neighborhoods are not simpler, even if a structure is very simple. So the classic example is a collection of complete graphs. So Kn is the complete graph on n vertices. If you look at the one neighborhood of any vertex, it is the whole graph, because everything is a neighbor of everything else, which means Geisman's theorem provides no simplification, right? Saying that any sentence can be evaluated by evaluating on its local neighborhoods doesn't help at all, because the local neighborhood is already everything. But on the other hand, complete graphs are actually very easy. They're evaluating first-order sentences in complete graphs is easy. It's just, the locality is not the right way to look at it. One way to look at this is that if I have a formula in the language of graphs and I replace, this is justifying this statement. I replace every occurrence of EXY by x is not equal to y. I get a formula in the language of equality, which is true if and only if the original formula is true in the complete graph, right? So this formula is true in n elements, or in fact, here's what I say. The formula phi is true in the complete graph on n elements if and only if phi bar is true in the edgeless graph on n vertices, so just n elements with no edges, or in fact, in any graph on n vertices. Okay. So what is this saying? One way of understanding this is that whether a formula is easy to evaluate or any kind of notion of tameness should still hold when you complement the graph, right? If you have a graph and it's easy, taking the complement of the graph, evaluating a formula is still easy because you can just replace every subformula EXY by its negation. But complementing a graph really changes the sparseness. The complement of a sparse graph is definitely not sparse, right? So if you take a collection of bounded degree graphs and take their complements, then then you get a class of graphs which is definitely not sparse. So we want notions of tameness which are invariant under operations like this. And more generally, we will talk about graph interpretation. So a graph interpretation is a pair of formulas, delta with a free variable x and epsilon with free variables x and y, which, interpreted in a structure, define a graph whose vertices are exactly those elements that satisfy delta and whose edges are exactly those pairs, AB, which satisfy the formula epsilon. So we say that a class of structures C interprets a class D, or D is interpretable in C, if there is some interpretation such that every structure in C, or every graph in D is obtained as the interpretation of some structure in C. Then there's an easy way of translating formulas from the language of graphs into A, so that the formula phi is true in G if and only if phi hat is true in A. That's the sort of, you would just replace occurrences of the edge relation in phi with epsilon, relativize all quantifiers to delta. Okay, I hope this is fairly standard. Okay, so this is what a graph interpretation is. We will actually be interested in a slightly more general notion, which is we call transduction. So we say class C of structures transduces a class of graphs if we can expand the vocabulary with some finitely many unary relation symbols and then give a graph interpretation in this expanded vocabulary such that D, every graph in D, is obtained as an interpretation of some expansion of a structure in C. Okay, so in a sense, this allows us to, these are sometimes called monadic transductions because, you could define them in sort of monadic second-order logic rather than first-order logic. But basically, before I do my interpretation, I'm allowed to arbitrarily color the elements of my structure in C. Okay, this allows for a richer notion of interpretation, which turns out to be very, very useful. As now I'm going to sort of give you a brief survey of results without proof on these tame classes of structures which are not necessarily sparse. So the first observation is transductions compose. If you have a class of graphs C which transduces a class D, and D transduces E, then C transduces E, right? You can just, literally you can compose the transductions by substituting in the formulas. And in a sense, if C transduces D, then what this means is that D is structurally no more complicated than C, because pretty much all the complication in D can be found in C by means of this first order formula. And I think this is kind of, it's meant at addressing the point that was raised that you may have structures whose Geifman graph is utterly simple because it's the complete graph, but they're structurally complicated. And that you recover by saying that they can transduce a complicated class of graphs. And the half graphs were mentioned, and that is exactly a typical example. So if you have a class that transduces the class of all graphs, it's pretty much as complicated as it gets. On the other hand, everything, any class of graphs which is infinite, transduces the class of all complete graphs. So this is, so the fact that transductions compose means that you have, a preorder on the classes of graphs with the simplest class at the bottom. If a class of graphs transduces the class of all graphs, it's maximal in this transduction order. It's as complicated as it gets. And because everything transduces the class of all complete graphs, the class of all complete graphs is as simple as it gets, right? It's basically the same as the class of graphs with no edges at all, right? Just, they are effectively the same thing. Okay, so we have a transduction order, and we now want to identify which classes are tame in this order. And here's an example. So the class of complete graphs is as simple as it gets, but the class of one subdivided complete graphs turns out to be as complicated as it gets. What are one subdivided cliques? So this one subdivided cliques means you really just, you take a graph Kn, which is the complete graph on n vertices. Let me just draw it for 4. And you subdivide it, which means for every edge, you insert a new vertex in the middle of it, which has a degree 2 vertex. This is the one subdivision of the 4 clique. So this is K4, 1. Okay. In general, you can define the R subdivision by replacing every edge by a path of length R plus 1. But, okay, so this is what we mean by the one subdivision of the n cliques. So consider the class of graphs, which are one subdivisions of n cliques. And the claim is this transduces the class of all graphs. Let me illustrate this because it's a good example of a transduction. So here's what we do. This on the left here is K5, 1, the one subdivision of the 5 clique. And here is an arbitrary graph I've chosen on 5 vertices. And I claim I can get this from this one by a coloring and then a first order interpretation. So what is the coloring? I use one color to mark the original 5 vertices of my 5 clique. Now I use another coloring, red in this case, to mark those edges which I want to keep in my graph, and a third color, black, to mark those edges I want to discard. And now a simple first order formula will construct this graph from this one, namely the set of vertices is exactly the green vertices here. 2 vertices are connected by an edge. If there's a path going through a red edge, you know, a path of length 2 going through a red edge between them, and that's all. Okay, and so you can see I can construct any graph I want on n vertices from a one subdivided clique on n vertices. Therefore, the class of one subdivided n cliques transduces the class of all graphs, and therefore, in terms of the structural complexity we're interested in, is as complicated as it gets. Now,
Excuse me, sorry.
yeah.
So in this kind of interpretation, you are allowed to put as many number as you like to the vertices which are put on the middle vertices, right? You're allowed to do that because you are using red and black in here. And
Right.
I assume that if you are allowed to do that, then you can easily say that we are working with edge-colored complete graphs, right? So because you're interpreting existing and non-existing of the edges with blue and with the red and black reds, right? So it basically you could have colored edges instead of adding some nodes in the between. You can initially you could have just colored the edges of complete graphs.
Okay, so let me. So here was my notion of transduction. A class C transduces a class D if there is some expansion with a fixed number of colors, so that I can interpret by first order interpretation D in the class of expansions of C, right? So now what I'm trying to argue is that there is a fixed class of graphs, namely the one subdivided n cliques. So this class of graphs is not a class of colored graphs. I'm claiming that this class of graphs is complicated because there is a transduction which constructs the class of all graphs from it. That transduction uses exactly 3 colors, right? I used red, green, and black.
Exactly.
So, and if I look at all the expansions of these one subdivided cliques, then from that, I have a first order interpretation, which gave me the class of all graphs.
Yeah.
That was the claim. So the point of this example was that this class of graphs, right, not colored graphs, but this class of graphs is complicated because by a transduction with 3 colors, I can construct the class of all graphs.
Exactly. Yeah. Thanks.
Okay. Okay. So a half graph, as was mentioned, is an example of a structurally complicated graph. A half graph of order n is the following bipartite graph. We have 2 sets of n vertices, and we have an edge from ai to bj if and only if I is less than or equal to j, right? So this is what it looks like. This is the half graph on 2 sets of 6 vertices. A1 is adjacent to everything above. A2 is adjacent to everything from B2 to B6. A3 is adjacent to B3 to B6, and so on, until A6 is only adjacent to B6. So half graphs are complicated in the following sense, that we cannot transduce the collection of half graphs in the class of complete graphs, right? I remember I said the class of complete graphs is as simple as it gets. In particular, it cannot transduce the class of half graphs. The proof, I mean, it's really the following observation. If you take a complete graph and you expand it with unary relations, any fixed number of unary relations, right? So remember, in a transduction, the number of colors I'm allowed to use is fixed. The number of, if I look at an expansion of a complete graph on n vertices with m colors, the automorphism group has at most 2 to the m orbits on pairs of elements, right? Because I have m unary relations, so there's 2 to the m different ways I could have colored a particular vertex. Any edge, I look at the pair of colors that appears on it. I don't know why I have 2 to the 2. It is, that's right. That's right. So I look at the pair of colors that appears on it, that's 2 to the m squared, right? Which is exactly 2 to the 2m. And obviously, once the pair of colors is the same, then there's an automorphism which will take me from from one pair with a pair of colors to any other pair with the same pair of colors. And the point is that this number is independent of n. It only depends on m. While in a half graph of order n, we can define a linear order of length n. And in this finite linear order, the number of orbits is bigger than n. And so it grows with n. And that shows that you cannot construct this half graph from a coloring of a complete graph with any fixed constant number of colors. Okay. So this shows that the class of complete graphs does not transduce the class of half graphs. On the other hand, the class of half graphs does not transduce the class of all graphs. And I mean, I'm not going to give you a full proof of this, but in particular, it doesn't transduce the collection of power set graphs, where a power set graph of order n is a bipartite graph on 2 sets, one of size n, one of size 2 to the n, right, labeled by every subset of n, where you have, sorry, that should be I as a member of J. You have an edge between AI and Bj precisely when I is a member of J. Okay? And you can show the class of power set graphs does transduce the class of all graphs. I mean, this is not very difficult. Okay, so, I mean, in this transduction order, I have given you at least 3 distinct elements. The complete graphs, which are the simplest, half graphs, and power set graphs, or one subdivided cliques, they're all equivalent because they interpret all graphs.
I'm sorry. By chance, isn't it somehow related or maybe just equivalent to the NIP stable and general class? Because
absolutely, it is, except because I'm allowing transductions rather than interpretations, it's a slightly different notion. But I mean, so we call these monadically stable and monadically NIP, and that is exactly where I'm going with this. I see.
But what I was wondering is that the argument that you mentioned, right, regarding the counting those automorphisms which was different from half graphs and the complete graphs, it somehow reminded me counting the types, right? Maybe you could just rephrase that in terms of the content, and then basically the half graph is just the unstable case. The general class, the complete graph is just a very simple case, but I mean just nothing. And the NIP case is, I mean, the for the power set, right? So
that's right. Except we're counting types in these arbitrary expansions with colors, right?
Exactly. Yeah.
But that is exactly what it is.
Okay. Thanks.
So now what I want to do is relate this a little bit to what I had on sparse classes. So say that a class of graphs is structurally nowhere dense if it's transduced by a nowhere dense class of graphs, right? So nowhere dense was defined in terms of sparsity with few edges. But structurally nowhere dense means in some sense, so this is addresses your point earlier. Now, the class of graphs may be dense, like maybe the class of called complete graphs, which is clearly not sparse. It's not nowhere dense, but it is simple, and it is easily transduced in the class of edgeless graphs, which are definitely sparse. So if you can transduce C in some nowhere dense class, we say it's structurally nowhere dense. We say that a class of graphs is monadically stable if it does not transduce the class of half graphs. And we say it's monadically nip if it does not transduce the class of all graphs, right? So this is exactly the notions you were saying of stability and nip. I'm giving them as definitions, and we call them monadically stable and monadically nip because we're using these transductions which use these monadic, additional monadic relations. So what is the relationship between these? Okay, it's kind of trivial to see that any nowhere dense class is structurally nowhere dense, right? Because it transduces itself. The complete graphs are an example of something that's structurally nowhere dense, but not nowhere dense, right? I mean, they have lots of edges, but they are simple. They're structurally nowhere dense. There's a theorem of Adler and Adler who showed that any nowhere dense class of graphs is in fact stable in a more classical sense. So in particular, it's also monadically stable, right? So stable meaning it can't interpret the half graphs, but so in particular, you show, well, I mean, yeah, you can't transduce the half graphs also. So any structurally nowhere dense class is also monadically stable because transductions compose. And any monadically stable class is monadically nip. That's kind of a sort of straightforward inclusion. Okay, so we have these kind of series of inclusions. So any structurally nowhere dense class is monadically stable. Any monadically stable class is monadically nip. In terms of separations, complete graphs give us a separation between structurally nowhere dense and nowhere dense, right? I mean, the half graphs give us a separation between monadically nip and monadically stable. We don't have an example of a class of graphs which is monadically stable but not structurally nowhere dense. And in fact, it's conjectured that the two are really the same. But this is an open question. Every monadically stable class is structurally nowhere dense. Okay. I mean, this would, if true, would say that this whole that this limit of sparse graphs we found, structurally nowhere dense, is actually a stability theoretic notion, which I think would be quite nice. So now there are some interesting inclusions or separations we can specifically say for sort of monotone and hereditary classes. So let me very briefly say what that means. So for structures in this A and B, we say, I'm giving this simply because I'm using this terminology in a slightly different way from the way it's often done in model theory. I'm borrowing graph theoretic terminology, but there's a difference made between a subgraph and an induced subgraph. I'm using that now I'm going to use the term substructure and induced substructure, even though what is commonly called a substructure in model theory is what I'm calling an induced substructure. So let me explain. For me, a substructure of A is something whose universe is a subset of A, and where every relation is a subset of the corresponding relation. And it is an induced substructure, if the universe is a subset and every relation is actually just the restriction, that should be B, a restriction of the relation in A to the universe of B, right? That's what we call an induced substructure. As I said, these generalize the term graph and induced subgraph as they're commonly used in graph theory. So we say that a class of structure C is monotone if whenever a structure is in C, so is every substructure of A. And we call it hereditary if whenever A is in C, every induced substructure of A is in C. Now, remember concluded the first part with this theorem, which said that the problem of evaluating first-order sentences is easy on a class of graphs. But by easy, I mean, sort of nearly linear time, subject to parameters. Easy on a class of graphs if it's nowhere dense. There is a sort of converse to that, which says that for any monotone class, if it's not nowhere dense, then first order satisfaction on C is hard, right? And now, what does hard mean? There is a formal definition in complexity theoretic terms, but I would have to, it would be too much of a digression to give you the definitions. But you have to make certain complexity theoretic assumptions and then show that there is effectively no algorithm which will do better than size of the structure raised to the power of the size of the formula or something like that. So for monotone classes, nowhere dense is the limit. And this is because monotone closure under substructure means if you have something dense in your class, then looking at substructures, you get something very rich, right? So if you have a sort of infinite sequence of dense structures, by taking substructures, you get something very, very rich, and things become hard. So for sparseness, when we're looking at sparse classes, it makes sense to look at monotone sparse classes. When we're looking at, the monotone closure of a sparse class is still sparse. But, you take the monotone closure of the collection of complete graphs, and you get the collection of all graphs. But you look at the hereditary closure of the collection of complete graphs, that's still the collection of complete graphs, right? Because an induced substructure of a complete graph is still a complete graph. Okay. So in some sense, this attempt to generalize this theory from sparse classes to not necessarily sparse classes using these notions of stability theory focuses on moving from monotone classes to hereditary classes, right? For monotone classes, we understand completely. The class is easy, tame if it's nowhere dense, and it's hard otherwise. For classes which are hereditary, the question is still a little bit subtle and open. Okay. Every nowhere dense class of graphs is monadically stable. I mentioned this before. But again, for monotone classes, there is a converse. Every monotone monadically nipped class is in fact nowhere dense. And this follows from the fact that if you have a class that's not nowhere dense, so that means there's some fixed radius R, so that for infinitely many n, the R subdivision of the n clique appears as a subgraph of a graph in C. This is pretty much from the definition of nowhere denseness. And we've already seen that once you have the one subdivision of an n clique or some subdivision, you can interpret all graphs. Okay. So for monotone classes, the picture is very clear. All these notions coincide. Nowhere denseness, structural nowhere denseness, monadically stable, monadically nip, they're all the same once your class is monotone. The conjecture for hereditary classes is that the evaluation of first-order sentences on C is tractable. So this is the notion of algorithmic tameness we were aiming for, if and only if C is monadically nip. This is a conjecture which is in some sense the running conjecture in the field. There are many people working on this. One direction has only very recently been proved. Again, subject to the usual complexity theoretic assumptions. This is a result due to Dreyer, Mellman, and Tarunchik. If a class is hereditary and not monadically nip, then the evaluation of first-order sentences on C is hard. Okay, so a hardness result has been proved. The other direction would mean showing that on any monadically nipped class, which is hereditary, but in fact, for the other direction, that maybe we don't even need the assumption of hereditariness. But for any monadically nipped class, there is a way to evaluate first-order sentences, which of low complexity. This is the conjecture. What do we know in this direction, on this algorithmic tractability? So for monotone classes, we know the result. If C is monotone and monadically nip, evaluation of first-order sentences is tractable, right? FPT means fixed parameter tractable. It's easy. This is because monadically nip is the same as nowhere dense for monotone classes, and for nowhere dense classes, this was the result of Grohe-Siebert's and Kreutzer. For edge-stable classes, this has been proved. I haven't defined what edge-stable is, but let me, I'll just leave this here. There's also a theorem of Bonnet that if you have a class which is monadically NIP, hereditary, and it's a class of ordered graphs. So this means structures in which you have two binary relations, a graph relation, and a linear order of the whole universe. For this class, they prove that evaluating first order sentences is fixed parameter tractable. So it is NIP. I know I have the word and there, but I don't actually have another result to follow this. So this is, as it were, advances towards this conjecture, and this conjecture remains open that any monadically NIP class admits an efficient algorithm, fixed parameter tractable for evaluating first order sentences. Okay, I think I'm at the end of what I wanted to say. So I just have a sort of concluding slide. The complexity of evaluation of first order sentences is a benchmark of the tameness of a class of finite structures. So in fact, I mean, I referred to tameness, I referred to preservation theorems at the beginning. There are many actual ways in which classes are seen to be tame, but one benchmark, which is commonly used, is how can you evaluate first order sentences without this kind of complexity blow up, which is of the size of the structure to the size of the formula. For monotone sparse classes, this has been completely mapped out. And nowhere dense classes are exactly the limit of this. For hereditary classes, this is the subject of a significant effort, and it kind of hinges on notions and methods borrowed from stability theory, usually combined with some hard combinatorics. The proofs that these stability theoretic notions, the examples I mentioned to you about monadically NIP ordered classes, to actually prove that you get the first order tractability requires, I mean, not just the definitions from stability, but doing some hard combinatorics with them. Okay, and that's where I want to conclude. Thank you.
Thank you. Very nice talk. Is there any other questions or comments?
Can I have some questions?
Yeah, of course you can.
Yeah, thank you. I mean, you mentioned some conjecture mentioning that if the monadically stable implies structural invariance, right?
Yes, what I call the sparsification conjecture.
Yeah, so it's in a way in the reverse side of the previous Adler result that you showed, right?
That's right.
So I was just thinking, how can one approach this one? So basically, you have to in the context of adding this additional predicates, right? You have to show that if there is some dense structure, very deeply hidden, minored in the structure, which means that it is not nowhere dense, then you will kind of find this half graph in terms of under the condition of adding these predicates, right?
Right.
So it is basically mentioning this.
Yes, though I mean, let me just say something. For monotone classes, sorry, I'm trying to find this. For monotone classes, right, we know this, okay?
Yeah.
Nowhere denseness and monadically stable are the same. So the conjecture is really for that this equivalence, well, actually, okay. So if you're not monotone, then in fact we can separate nowhere dense and structurally nowhere dense. I mean, that's trivial because you just take the collection of complete graphs.
Yes, yeah.
It is not nowhere dense, but it is structurally nowhere dense.
Exactly.
So the connection is between these two. The claim is that this holds more generally rather than, I mean, again, in the absence of monotonicity, these two are also separated. Monadically stable and monadically NIP are different.
Yeah,
The conjecture is, and these two are different, but the conjecture is that these two are the same. So
yeah, exactly. So basically what you have to look for is just constructing a pattern of half graphs using a dense graph, right?
Using a dense graph.
But provided that you are considering adding those predicates, right? The color predicates. You are doing that in that context. So assume that you start with a colored structure with a dense substructure as a minor, and then you start to somehow develop a technology for counting the types, right? Because there is a hidden structure or that the types are able to somehow, because types are somehow more manageable than the structure and minor and certain things, right? Because basically you can just write down some sentence and so on. So if you are able to somehow count the types, and there are sufficiently many, then with the same coloring or maybe just some modification of that, then it is likely that you end up with constructing a pattern, right? Out of these types. What I'm saying is that what if we try to somehow adopt the technology of in the infinitary setting, namely larger of the type space, equivalent to emergence of this half graph patterns in the finite setting, right? What's provided that we are careful about these number of predicates which are added and control that, right? In a way. So, yeah, I was wondering if it is just adaptable.
Possibly, though. I mean, yeah. I mean, I don't have a definite answer. So, but I mean, I think this is certainly something to look at. I mean, I don't know all of the kind of techniques that work in the infinite setting, and I mean it's quite plausibly actually many of I mean, this conjecture could be reformulated as one about infinite graphs by looking at limits, right?
Yeah.
So yes, I mean, I think
maybe ultra product, or maybe ultra product, right?
That's right. Something like that. Yes.
Because if you look at the ultra product of this structures, then you will get a pseudo-finite structure, and we know some good things about the stability of pseudo-finite things, right? And then possibly certain kind of information could be transferred to that setting, and then automatically use that kind of stuff or there, and then return back to the initial setting.
Yeah.
So maybe just some sort of limit is helpful here.
Yeah.
Other questions?
So thank you.
Possibly, can we have VC dimension for monadically classes? Is there any?
Yes, there is work relating this to VC dimension as well. But I hesitate to say, because I'm not sure I can remember the exact results. But yes,
there are some connections.
There are results which connect this as well. Yes.
Right. Okay. In case there is no other questions, let's thank the speaker for very nice and very general and comprehensive talk. Thank you very much.
Okay. Thank you very much.